So it was just talking. I should have realized everything was a little bit out of focus. Oh, that's I'm like, okay, and then like a couple weeks later, I'm like, I know it. She's like, what?
Okay, any questions on what we're doing? Any questions on what we're doing? On the homework or anything? No? Everything's all right? Raina, do you have a question? No? Okay. Yeah, Nua.
I have a question.
Yes, go ahead.
Can you go through like negative roots?
Negative roots. Do you mean the roots of negative numbers or the negative
Like
roots?
For the homework.
Yes.
Number 66 was like say that this equation cannot have 3 negative roots.
Cannot have 3 negative roots. Okay.
Can you just explain that?
They just meant like it cannot have 3 roots that are, that are negative numbers. And probably, does anyone have a?
Yeah,
So
no, I got that.
you got, so you got it, but you didn't.
I just don't. Can you go over the roots idea?
Okay.
Like finding a root.
Okay.
Through rule 0.
Okay. So and that's sort of problem. Basically, it probably had to do with like the like the second derivative or something like that.
Yeah.
Right. What? Can somebody tell me the problem? 66. Okay, thanks. Okay. So this guy here, ax squared plus b, and it said show this p cannot have 3 negative roots. Okay. So roots is of course the same thing as a 0, right? A place where it intersects the x-axis, right? So you have this polynomial, and it's saying that this is a cubic, right? So it could look something like this, right? It could look something like this, but they're saying that can't happen, right? A cubic could look like this, and it could, some cubic could actually have 3 roots, 3 zeros that are all negative, right? But they're saying that can't happen. Okay. Did anyone figure it out? Yeah, Elise.
I don't have my paper with me, but I think what I did was I found that the one in the middle had to be at 0, and so, or one of them was positive.
Okay.
Or something.
One of them had to be positive. So one had to be positive. Do you remember what kind of argument you used or how you showed it?
I think it was. I don't remember.
Okay, that's okay. So
I just remember that one of them was positive.
okay. So yeah, Evan.
Well, do you want me to say how I did it?
Yeah, go ahead.
Okay. So if you like tried to do it out, so like your roots were x plus 1, x plus 2, x plus 3, so that would make it -1, -2, -3. Like you would have to have an x term, like an x to the first degree term somewhere in there, and since there isn't, like you couldn't do that. You'd have to have one positive and one negative to cancel it.
Okay. So you basically made up a function, right? You said let's look at x minus a, x minus b, x minus c, or something like that,
Yeah.
and you worked it out and you showed that that there's going to be an x term in there to make it cancel. Okay, that I think that should work. That should work. That's good. I think I have to take a look at it. But a way that's maybe more along the lines of what we're thinking is what we're doing recently is to use Rolle's theorem, right? You say, okay, well, suppose P has 3 negative roots. Suppose it does have 3 negative roots. Well, then what would happen? If you had 3 negative roots, then what can you say? If there are 3 negative roots, something like this, then what can you tell by Rolle's theorem? Yeah, what?
If there's 3 negative roots, can't you say that there's 2 places in the function where this derivative is 0?
Yeah, then there's going to be 2 places, and they're both negative, right? Then there are 2 places, two numbers, 2 points, where P prime is equal to 0. Okay. So there's 2 places where P prime is equal to 0. Okay. So P prime, 3x squared plus 6 ax. Sorry, 2ax. X. Okay. Right. Then what? Or if there's 2 places where, if there's 2 places where P prime is 0, right? And further, they're negative, right? There are 2 negative points, right? There are two points, and they're both smaller than 0, where P prime equals 0, right? Okay, if that happens, suppose that happens. So you know that P prime, right? P prime has to intersect in P prime has to intersect in 2 places that are beneath the x-axis, right? What would that tell you? Yeah, Jennifer.
Well, if you just look at the function, that can't be true.
Yeah, actually, yeah. So if you look at the function, you see that one of the roots is already x. One of the roots is x. I'm sorry, one of the roots is 0, right? So you see, well, so there should be, if P has 3 negative roots, then that means that P prime has 2 negative roots also. That P prime has 2 negative roots, right? But if you look at P prime has 1 0 root, and then at most 1 negative root, right? So it's impossible. So this is impossible, right? Because P prime doesn't have 2 negative roots. It has at most 1. So this is sort of a roundabout way of seeing that this cannot happen. You say, suppose it does happen, and then you end up with craziness. Okay. And you say, okay, well then that couldn't have happened. Evan's way, I think, will probably turn out to be more instructive, but this is one way, and this is a way that uses Rolle's theorem. Does that answer your question, Nora? Maybe it doesn't. Does it answer your question?
Yeah, it does. I
That sounds like it doesn't.
It's like a little bit. I can talk to you about it later.
Is the question what is a negative root, or?
Kind of like how you get it from that equation 3x squared plus 2ax.
How do you get the roots from it?
Yeah.
Like suppose somebody gave you this, and they said, what are the roots of this thing? right? Well, you'd say, well, I'm going to factor.
Yeah, so
right?
I factor.
So you just factor, you get the x, you get 3x plus 2a, right? Right. So this equals 0. This will be equal to 0 if and only if x is equal to 0 or 3x plus 2a equals 0. Okay. The reason is that the only way there's something called the zero product property that if you have two numbers, then the only way that you can get a 0 is if one of them is 0, right? So if somebody says, when does this thing equal to 0? You say, well, I just need to check the parts, right? When is this equal to 0? Well, that's x is 0. When is this thing equal to 0? Well, x is going to be negative 2a over 3, right? So x is 0 or x is equal to negative 2a over 3. Okay. So that's how you do it.
Okay,
Right?
yeah.
You factor it, and then you say by the zero product property, this is going to be 0, whenever one of the factors is equal to 0. The trouble is factoring, right? Because if somebody gives you a quadratic, well, it's easy to factor. You use the quadratic formula. If somebody gives you a cubic, can you factor it? There is something called the cubic formula, and you can use it to factor. There's even a formula for fourth degree polynomials. And these used to be secrets that people would hold in the 16th century. Like there's one school, and they would only teach these formulas within their school, and feel superior to all other schools of mathematics. And then like somebody would steal the formula, and then become popular, common knowledge, and then everyone would be angry about it. So there's some I don't know enough history. This is probably not even true, but I'm going to say it anyway. Okay. But there is actually a pretty famous story, which I'm pretty sure is true, which is about the fifth degree formula. Okay, so people tried to get this fifth degree formula. Nobody can do it. Nobody can do it. Nobody can do it. Okay, and then comes along this guy, Galois. So Galois is a brilliant young mathematician. He gets killed at the age of 21. The story is that he's involved in politics and in French politics, and for some reason he's set up. He's basically forced to go through with a duel. He knows he's going to lose the duel, and he knows he's going to be killed at the duel. So he spends the entire night writing down all of his mathematical ideas. He's actually been sort of shut out by the mathematical establishment. Nobody will listen to him. But he spends a whole night writing down his ideas, and he has this. They still have his letter. It's like this massive scrawl of several pages of ideas. And the next morning, he goes to the duel and is killed. Basically, the next century is spent deciphering Galois' last letter, and he basically laid out a whole new system of mathematics through which you can show that it's impossible to have a formula for the fifth degree and above. It's impossible. There is no formula, and Galois was able to show it before he was killed at age 21. Okay. Okay. So let's get back to the mean value theorem. So remember what that tells you. It says, well, if you have a function on AB and it's continuous, then what? Somebody tell me. Then what? You have some function AB right? Here it is, it's continuous. Needs to be differentiable, right? And differentiable on AB. Clearly overcome by telling the story of Galois. Yeah.
There is a place C where f prime of C equals f of B minus f of A over B minus A.
Right. Okay. So there's a place where the slope, the slope of the tangent line equals the slope of the line through the endpoints. Right. There's a place where the slope, there's a place C, where the slope of the tangent line at that point equals the slope of the line through the endpoints. And we finished up with last time with the proof of this. Okay. Now, this, you can think of this as, you can find this point where the slope equals the slope of that line, right? But you can also think of it in a reverse way. So it can be used backwards. So mean value theorem can be used in reverse in some sense, right? That is, the slope of that line has to equal the derivative, has to equal the slope of the tangent line at some point. Okay, so right, if somebody tells you about the derivative, then they're telling you about the slope of that line. Okay, so you can use it in a sort of reversed way to get information about the function. Okay, so there are a couple of corollaries to the mean value theorem. So corollaries means just like simple consequences. The first is the following. Say f is differentiable on AB, and f prime x is 0 everywhere. Okay. This triple equals sign means is constantly equal to. Okay. So is constantly equal to. Okay. So if the function is differentiable and f prime x is constantly equal to 0, then what does that tell you about your function? Can somebody tell me what the conclusion will be? Think about it for half a minute and see if you can tell me. Okay, talk to somebody nearby.
I mean, is this the same thing?
Okay. Okay. Who has something to say? Who has something to say? Raina first.
So if f prime of x is constantly equal to 0,
Yeah.
then f would be a constant.
F would be a constant. So f is a constant function. Sarah, what did you want to say?
I was going to say f of B equals f of A.
F of B equals f of A, which is also part of it, right? If f is a constant function, certainly f of B is equal to f of A. And so I'd like maybe Sarah, how do you know that f of B equals f of A?
Because f prime of C is always going to be 0, so
Yeah.
you know that the other side is going to be 0.
Yeah. Yeah, exactly. Okay, so you say, well, look, we know that f of B minus f of A over B minus A equals f prime C for some C. Right? For some C in AB. right? So we know by the mean value theorem that f of b minus f of a equals f prime c for some c in between, but f prime of c is 0, right? F prime of c is 0. We assumed we were told that f prime of c is everywhere 0, right? But that means that f of b minus f of a must be equal to 0, right? Because you've got this fraction equaling 0. That must mean that the numerator equals 0, right? In other words, f of b and f of a are the same. Okay. But then you notice that it's not just a and b. It's any 2 points, right? It's any 2 points. So in fact, for any 2 points, x1 and x2 in AB, we see that f of a, f of the first guy equals f of the second guy by the same reasoning. In fact, by the same reasoning, if you take any 2 points, they're going to be the same value, right? Because of this, right? You look at those 2 points. Well, the slope between those 2 points, the slope of the line between those 2 points must equal the slope of the tangent line somewhere. But the slope of the tangent line is 0 everywhere, right? So f of x1 must be f of x2. Okay, and so it's not just that the endpoints, not just that the line from beginning to end is flat. Every secant line is flat. So it's a constant function. Okay. So f is a constant function. Okay. Any questions about that? Any questions? Everyone following? Okay. 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 Corollary 1.5. Okay. So if f and g are differentiable on AB, and f prime equals g prime everywhere. So these guys are equal to each other. F prime and g prime are the same. Okay, maybe it's better for me to say like this for all x. F prime and g prime are the same. Can anyone figure out the conclusion?
The functions run parallel to each other.
The functions run parallel to each other. What do you mean run parallel to each other?
No matter what degree they are, they're constantly going to be equally spaced from each other.
They will be equally spaced from each other. So then, f of x minus g of x, or f of x equals g of x plus some constant. Or maybe let me say it like this: f of x minus g of x is constant. Right. One guy is the same as the other guy, but plus some fixed number. Right? The picture is like this: A, B. You're going to end up seeing that one guy is the same thing as the other guy, but just plus some constant. Right? At whatever point in time, they have the same. They have the difference stays the same. The difference is constant. Okay. Okay. Why? Can anyone see why? I'll let you think. Why? Why does that happen? Can anyone see? Oh yeah, Kayla.
Because when you take the derivative of a constant, it's just 0.
Certainly the derivative of a constant is 0. So if we know that they differ, by constant at the beginning, then certainly when you take the derivative, then that derivative is going to be 0. But that's the conclusion, right? That's the conclusion. It's not the hypothesis, right? So you want to start from here. Suppose you know that the functions have the same derivative. How do you know that they're going to differ by a constant? How do you know that they're going to differ by a constant? If you have two functions that have the same derivative, how do you know that they're going to be differing by a constant? Wynn, go ahead.
So when you take the derivative of something, constant are in terms of 0, like you said, but so in the end, it's going to be the same slope and parallel lines are the same slope. So I guess when you take the derivative, the constant gets left out, meaning the derivatives are the same.
No, it's sort of along the same thing. Here's the hint. Think about part 1. Part 1 says that if you have any function whose derivative is 0, then it must be a constant. Okay, so here's the hint. Try to use part 1 to get part 2. Okay, take 1 minute and see if you can get it. You have something, Evan? Or you have a question?
Yeah.
No. Okay. Okay. Cool. Okay, talk to somebody nearby for just a few minutes, a few seconds.
So that means that just like when you did that international fee.
Cole, you should come up and talk with somebody. Go and talk with somebody. Either talk with Noor or with
So like this is, and that's like this
or Isaac. Okay, anybody get it? Evan, you had your hand up video. What do you think?
Well, I wasn't really using mean value theorem, but the way I thought about it is if the derivatives are the same, that means that the functions are the same, and that the only difference in the function would be whatever constant it would be, which is why.
That's sort of what we're trying to say here, right? So you're in some sense you're saying what we're trying to show, right? You're saying, well, if the derivatives are equal, then the functions must differ by some constant.
Well,
right?
I'm saying that the functions are the same, and that the only
except for some constant.
Yeah.
That's what this says, right? The functions are the same except for some constant.
Yeah, but like if you just go backwards from the functions, then like you don't need to use mean value theorem to like understand it.
But you've given a circular argument, right? You're saying that if the derivatives are the same, then the functions differ by a constant. Because if the derivatives are the same, then the functions differ by a constant, right? Right. This.
Well, I don't get what you're asking us to do over there.
Okay.
Like,
Okay, that's all right.
just like a logical conclusion that doesn't need proof.
Doesn't need proving. Doesn't need proving. Okay.
Why do you need to prove that? That's just like.
Why do you need to prove that? Yeah. Why do you need to prove that?
That's like logical. If A equals B, then like, or A prime equals B prime, then you just get the conclusion.
Then you're saying that this, as long as functions are the derivatives are the same, then the functions differ by a constant. The opposite, I think, is completely obvious, right? If the functions differ by a constant, right? If the functions differ by a constant, right? You have one function, and you have some other function, which is the first guy, plus a constant, right? Then when you differentiate them, right, f prime and g prime are the same. That's obvious, right? But the other direction, if you have two functions whose derivatives are the same, then they must differ by a constant. That's a different statement.
I don't see why that's not obvious.
Okay.
Because it's just
Let me-
saying that they're the same function.
It's not saying they're the same function. It's saying that they have the same derivative.
Yeah, but if you go backwards, you're gonna get the same function, and then
How do you go backwards? What is this going backwards?
okay, so like if your derivative is x, I mean I'm not trying to say it with integration, but like if you have x as your derivative, then you know that your original function was 1/2 x squared.
Let me give you an example. Okay, so yeah, you might think this doesn't require any proof. Let me give you an example of something. So there is a function. So there is a function where the derivative is 0 100% of the time. The derivative is 0 100% of the time. Okay, so if, you know, in terms of time, this function, the derivative is 0 100% of the time. And its function, it's a continuous function. Okay, and it's differentiable. Again, it's differentiable 100% of the time. Okay. So, but this function at time 0 is 0, and the function at time 1 is 1. Okay.
Is it step function?
It's a continuous function. It's a continuous function. Okay, so this is something called the Cantor ternary function. Okay.
What does that look like?
I think you have to Google it to get a good picture of it. Okay, but you should be saying, like, I heard somebody say, what? And that's actually the right answer. That's actually the right answer. Who said what? Okay, good. I think I'm just going to give you a bonus point for the what. Okay, because that means that you actually understand what's going on. Because this is crazy, right? Right? This is impossible, right? This seems like it's impossible. You have a car. The car's velocity is 0 100% of the time. The car doesn't teleport, right? It's a continuous car. It doesn't somehow vanish and then appear in some point, right? That's but it doesn't, you know, its speed is 0 100% of the time, but it starts up at time 0 and it ends up at 0. It's here, and an hour later it's a mile away. Okay. Okay. So the moral of the story is that functions are not cars, and that things are maybe not as completely obvious as they might seem. Okay. So in fact, we do need to justify this. Did anyone think of how to do it? Anyone think of it? Okay. So here's one way of thinking about it. So you could say, well, look, consider the difference, f of x minus g of x. Consider the difference. Do you have a picture of it?
Yeah.
Yeah.
It doesn't seem very helpful.
Okay. Okay. Yeah. So, if you want, I can talk to you more about it, but it's a little bit complicated. Okay. So consider this function f of x minus g of x. What can you say? What do you notice about it? What do you say about the derivative? This is not anything deep. What do you say about the derivative?
What can we tell about the derivative?
Yeah.
Which part?
Of this function here.
Can we use the information about it?
Yeah. Yeah. F prime is g prime. So what do you know about the derivative?
Equals 0.
The derivative is 0. Right. Then f prime minus g prime is equal to 0, right? And so from the previous thing, what do you know about it? What can you say about the function? Elise?
Would it be parallel? same tangent, same slope of the tangent.
That's true, right? So that's what we're saying here, that at every point, the slopes of the tangent lines are the same, right? The slopes of the tangent
So
lines are
would
the
it
same.
have, I mean, could they potentially have the same constant? Like they could either have different constants.
So, Sarah, please? Sorry.
I was just
Sorry.
like looking.
Yeah, just,
when you look,
I'm sorry.
Yeah. Going over there,
Yeah,
because
just,
there you
just
have.
use this thing here.
Yeah.
Use this thing here, right?
Exactly.
The
So
derivative
there
is
you have-
0. So what can you say about the function? The function is constant, right? So then f of x minus g of x must be a constant. Okay. And that tells you that f of x, right, is actually g of x plus some constant. So you can prove this. In one way of showing this is using the mean value theorem. Yeah, Elise.
So does that mean that one of them doesn't have a constant?
No, they could both have constants. It's just that when you look at their difference, the difference is a constant. So maybe one could be sine x plus 1, the other is sine x plus 2.
So it's just in relation to each other?
That's right. That's right. If you look at their, one is the other guy plus something.
Mhm.
Yeah, it's not saying that this one doesn't have a constant. It may well have. Okay. Yeah. So yeah, this trips up. I think people get stuck on this point every year, but you have to understand that. Okay, so let me put up an example. So here's what we can do now. Here's what we know now. Okay. So suppose you know that f prime of x is 2x. Okay. And you know that f of 1 is 10. Okay. And somebody asks you, what is f? What is f? Somebody asks you, what is f? Take half a minute and tell me what you can figure out about f. Okay, turn to somebody nearby and say, I think f is, I can say this about f. Okay, Elise, what can you say about f and how? How do you know?
So f of x would be x squared because it's like backwards, and it's just a power rule.
Okay,
The power
so,
rule, but backwards.
okay,
And then if you plug in the x, it has to equal 10 if you plug in 1, and so the constant has to be 9.
okay, so, so maybe x squared plus 9, right? Okay. Okay, so f of x is x squared plus 9, and the reasoning goes like this. You say, well, look, so I say that f of x must be x squared plus 9. Okay. You say, why? Well, I know that f prime of x is 2x, right? And if I look at another function, so if I look at the function x squared, I see that the derivative of that is also 2x, right? So here's some other function. I look at these squared. Looking at this 2x here, I think, well, I know another function. I know a function whose derivative is 2x, right? So the way you're thinking is, I know another function. I know a function whose derivative is 2x, right? Namely the x squared function. Okay. So then what do you say? These two functions, so pay attention here. This is important. Everybody misses this. Everybody misses the significance of this. Okay. You've got one function whose derivative is 2x. You've got another function whose derivative is 2x, right? So what does that tell you? So f of x must be this guy plus a constant. Right? That's the only thing it could be. There's nobody else in the world it could be. Okay. By the corollary. Okay. There's nobody else it could be. So you might, if you're suspicious, you might think, well, maybe there's some other function in the world whose derivative is 2x, right? No. Okay. So. Okay, the thing is that there's no, right, f of x has to be this function plus a constant. Okay. It can't be anything else. So, and then you just work it out, right? Since f of 1 is 10, we know c must be 9. Okay, so f of x must be x squared plus 9. There's no other function that'll work for this. Okay, and the reason for it is the corollary. Okay. These two functions have the same derivative, so they must differ by a constant. Okay, and then you see that constant has to be 9. Yeah, Elise.
So why do we have to use the comparing it to g of x equals x squared? Like, why is it that we use another function in order to prove that? Like, why can't you just do it with only the f?
Okay, so sort of what you're saying is this. You're saying, well, f of x, f prime x is 2x, right? And then you're saying, so f of x is x squared, right? Right. So f of x is x squared, but so the question is, this may seem kind of strange, but you'd say like, well, how do you know that it's x squared? All you know is rather that it could be x squared, right? All you know is that it could be x squared, right? But what the corollary tells you is that it has to be x squared plus a constant, okay? Right? So, everybody gets this wrong because you've had calculus before, and for some reason you think, well, it has to be x squared plus c. Okay. How do you know it has to be x squared plus c? How do you know it has to be x squared plus c?
Only if during the integration they give you a number that plugs out. If they don't give it to you, if the integral doesn't give it to you, then you know it's c. But if they do give you a number, then when you plug it in, it'll give you some value.
So how do you know that it has to be of this form then? How do you know it has to be of this form? And the reason is, and you say, well, we do integration. Well, how do you know that the integration works? The reason is this corollary. Okay, the only reason you know that is because the corollary tells you that if you have another function, that if you say, well, look, I have this other function, g of x, which is x squared, and g prime x is 2x. The corollary tells me that these two functions must differ by a constant, and so this has to be x squared plus c. That's how you know it. Okay. Okay. So I'm making a big deal about it. because for some reason everybody seems to miss this point at this point in the course. This is how you know it, right? The only reason you know that f is x squared plus c is because of the corollary. Okay. But yeah, I guess it. Okay. Okay. So last corollary, corollary 2. Say that you have some function on AB, and it's differentiable. Then f is increasing. No. Whoops. Suppose that f prime is always positive. Okay. F prime is always positive. Okay. Then f is increasing on AB. Then you've got an increasing function. So this is again another corollary of the mean value theorem. So here's A, here's B. X1, X2. Can somebody explain this to me using the mean value theorem? Yeah,
Well, if f is increasing, that means f of b would be greater than f of a. So the difference between so f of b minus f of a can't be 0. It'll always be greater than 0.
Yeah, good. Okay, so right, you say, well, look, again, you're going to use the mean value theorem in reverse. You say, well, look, by the mean value theorem, if I look at, say, f of b minus f of a over b minus a, that's going to be the derivative somewhere, right, for some c in ab. Okay. But again, you know that the derivative is positive. But the derivative is positive, and so you know that this thing is bigger than 0. Right? This thing is bigger than 0. Right? That's to say that the slope of the line between those 2 points is 0, and so this guy on the right must be bigger than the guy on the left. Right? Or you just multiply both sides by b minus a. Right? Then f of b minus f of a is greater than 0. Right? In other words, f of b must be bigger than f of a. Okay. So what that shows is that if you look at the endpoints, the one on the right must be bigger than the one on the left. Right? But again, you can say this, but again, this works for any pair x1, x2, right? If you take any 2 points here, then the one on the right has to be bigger than the one on the left, right? And so your function's going to be increasing. Okay, that's it for today. So I'll send out a homework later. Right now, and then in the afternoon between 1:30 and 5.
Can I come in and talk to you then?
That'd be great. Okay, that's it.